Okay, so this lecture is dealing with waves, right? You've all seen a wave. You go to a football stadium or whatever, right? And the people here, like all of a sudden they all stand up, right? And then they sit down, and as they sit down, the column here starts standing up, then this column. So the column that's standing up kind of moves across the stadium and makes its way around, right? That's a wave. So the question is, in what direction is matter moving as this wave traverses the stadium? What is actually what is it that's moving across the stadium?
Nothing.
Good point. It's not matter, right? Because it's not as if you are getting up and moving all the way across. It is not energy either, because in this particular case, in this particular wave that we're talking about, your energy is not transmitted to him. The energy that you use to rise up and come down is different from the energy that he's using, which is different from the energy that she's using. So in this particular illustration, what is actually happening is it's coordinated motion. It's actually information that's traveling. Isn't that really interesting? It's information that's traveling, that's modifying the local behavior of the matter in that particular spot. However, there are different. That's not the case necessarily with all waves, right? And we'll see some examples as we move on. Okay, a sine wave. You all know what a sine wave is. Does anyone in this room not know what a sine wave is?
I don't know.
Extra credit to you for speaking up, right? That's awesome. A sine wave is a wave that looks like a sine. Okay, that was a joke. Okay, I'm totally kidding. Okay, so a sine wave is a wave that looks like this. It starts over here, it goes up to the top, right? So you can see it's oscillating gently from the bottom to the top, to the bottom, to the top, to the bottom, to the top. It has a smooth kind of a curve, and it's called a sine wave because the sine function, S-I-N-E, theta, right? Function on your calculator or your graphing calculator will, if you plug that in and say, hey, change theta and plot y as a function of theta, you will end up with a plot that looks like this. So if I were to draw, right, an axis here, so y equals sine of theta or sine of x, let's say sine of x, and along the x-axis is x. Sine of x at x equals 0 would be 0, at x equals 90 degrees would be 1, at x equals 180 degrees would be 0, at x equals 270 degrees it will be minus 1, at x equals 360 degrees it will be 0, and then it would keep continuing like this as you increase the angles, right? You can actually plug in these numbers into your calculator and actually calculate those numbers and plot them. So this is called a sine, S-I-N-E wave.
Always move the same distance from each other?
Yeah.
It's always the same distance?
Yeah, from here to here is the same distance always in terms of angle.
What about on the y?
The y-axis is called the amplitude, and that is also the same for a given wave if there's no damping of the wave, and we'll see what that is, right? So in this case you can see if you had a like a spring with a ball attached and this like a pen attached to the ball, and you get this oscillating back and forth, and you have a long sheet of paper that you're gradually gently pulling, that pen will draw a line that looks like this, and that's how you create a sine wave, right? Okay, so here's the middle point of the wave, the dashed line in the middle. The amplitude is the distance from the middle point up to the peak. That's the same as from the middle point down to the trough, the bottom of the wave here. That's the amplitude. The wavelength is from any given point on the wave to the equivalent point, next point on the wave. Yes, Madam Zoe.
It's like when you're counting contractions from the beginning of one until the beginning of the next one.
Yes, that's an easy way to understand it. Extra credit to you. So if you look at let's say that the beginning of the wave is here in this chart, or this plot here. Beginning of the wave is here. So notice that from this spot, what's happening is we're moving upwards to the peak. The next place where we are at the 0 axis, along the x-axis, at the 0 point, along the y-axis. So we are sitting on the x-axis, and we are ready to move up. The peak is right here. So wavelength is from this spot to that spot. So this distance from here to here. We could also do it from the place where it's going down, from here to here, or we could do it from the peak to the peak, or from the trough to the trough.
No, are those always going to be the same?
They will always be the same, right? For a sine wave,
Okay.
right? Okay, so that's the wavelength here. Now we talked about this. Remember the bouncing electron? What happens when I bounce the electron? It went higher in pitch, right, in frequency as I increase the number of. That's totally awesome. Extra credit. And I heard somebody else speak up. You maxed out? Great. Then because you maxed out, extra credit to you, right? And I heard somebody else speak up too. Whoever spoke up, extra credit. Okay. Was it you? No. Okay. You just looked like you had spoken up. So anyway, remember that if I had an electron and I bounced it once, it sent ouch, 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 touch, right? So you notice that as I bounce it faster, higher frequency, the pitch goes up. So the same thing, guitar, right? The different strings, the string that's the tiniest, right? The thinnest one, and you pluck it, you typically get a high pitched sound compared to the fat, all wound up string. Same thing with the piano, right? If you hit the strings that are to the extreme left, like you're facing the piano, yes, that's the fattest strings, right? And they have a lower frequency, which literally means that the wave that's traveling in that string is traveling with a lower frequency than the wave at the right hand side of the piano where you hit it, it goes very tingy kind of sound, right? The frequency is higher. So now, as electrons are bouncing up and down, every time the electron is bounced, it gives off a peak, if you will, of an electromagnetic wave. So the electron has an electric field. When you bounce it, the electric field I feel a disturbance in the force, right? So a disturbance in the electric field. That disturbance is what we call the electromagnetic wave. So in a radio antenna, for instance, like a radio transmitter, what happens is electrons are bopping up and down with a certain frequency, and so they're creating electromagnetic waves that are traveling outwards with that same frequency. And that's how you create radio waves. So in this case, electrons in the antenna are bouncing at 940,000 times per second. So by the time you say 1 Mississippi, that poor electron has bounced up and down 940,000 times. So it gives off a wave that is 940 kilohertz. So if you look at your car radio and you see whatever frequency, right? Either kilohertz or gigahertz or whatever, then whatever frequency that you're reading, if it is 940 kilohertz, that means there's an electron somewhere that's bouncing up and down that many times, so that you can hear your music.
Not related, but in the antenna, how do they get them to bounce?
Good question. What you would do, let's say this is the antenna, is you can apply a voltage across the antenna. So a positive voltage here. So the electron, say if you have a positive voltage here, all the electrons are sucked up towards the top. Now as soon as, right, like a fraction of a second later, you switch the polarity. So now it's a positive voltage here. All the electrons that ended up here now are running down here.
So it's kind of like switching a light switch on and off?
Yes, it's very similar to that,
really,
right?
Really fast.
Yes.
Okay.
So 940,000 times per second, you switch the polarity.
Wow.
And that causes the electrons to oscillate back and forth.
Wait. Then would that be like, for example, we have over here, off of User Mountain, you have the giant antennas. So the big circle things, is that what they're...
I think there may be microwave antennas.
Yeah, those are microwave.
Okay, so they're doing exactly the same thing. What the microwave antennas has electrons that are oscillating at a microwave frequency. Microwaves, 2.5 gigahertz ballpark. So 2.5 billion times a second. So those electrons are way faster than this, right? And so it's putting out microwave energy.
I actually work on User Mountain. They actually have 3.6
gigahertz. Okay.
6.8 gigahertz.
Okay.
And 14.9 gigahertz.
Cool.
So
Extra credit.
Essentially, so with that, it's turning on and off 14 gigahertz.
Yeah.
14 billion times.
Yes. Now I have to
switching the polarity.
Yes. So I have to change the analogy a little bit. We're not really switching it on and off. What we're doing is let's say this is the positive terminal from our battery. What happens is, let's say I'm hooking this up to this one, right? So this is positive. Then I switch it here. Then I switch it here. Switch it back and forth, very, very, very fast, right? And that's what creates so it's kind of like switching it on and off. We miss you.
What you were saying about how it's switching the polarity and making it bounce up and down makes sense to me. But what about when you're listening to the radio and it's picking up that certain frequency? So it's picking up a frequency already, and then it can create another frequency to create the sound?
You're talking about the receiving end?
Yeah. Well, 'cause it has
No, I want to understand your question. What we talked about here is the transmitting end. So you're asking a question about the receiving end.
yeah,
Is that
like
correct?
she was just saying about the antenna.
Yes. Okay, good point. So in the transmitting antenna, this is the antenna associated with the radio station, the electrons are zapping up and down and sending out this wave, right? So this wave is an electromagnetic field that's transmitted through the atmosphere. Now let's say this antenna is my little radio with its antenna, or your cell phone with the antenna that's built in, or your little sticky uppy thingy, right? that cell phones used to have, right? So yeah, they don't have them anymore because somebody came up with a way of putting the antenna inside the cell phone, right? As a long wire that kind of goes around the inside or the outside. So here, let's say this is that antenna. What happens is the electromagnetic wave is traveling, right? As it travels here, it's a disturbance in the electric field. So as it comes across this antenna, the electromagnetic wave creates a positive, negative. It creates a positive voltage on this side of the antenna compared to this side. So the electrons in the antenna, they're just sitting around minding their own business. All of a sudden, they feel this urge to move in this direction. But then this electromagnetic wave, as it comes, it keeps flipping back and forth, like this. So it comes like this, pushes the electrons up, flips, pushes it down, flips. So as the wave keeps going through, right, it's flipping. So if you look at the wave like this, as the wave travels across the antenna, when the wave is coming across the antenna, it's like this, it's pushing the electrons up. So the wave keeps moving, and now the electrons are pushed down, then they're pushed up, then they're pushed down. So what happens is, in the antenna, now you've got the electrons moving up and down, which creates a voltage which you then sense and amplify basically to them.
So the antenna or the thing from the radio station, whatever that's called, the tower from the radio station is creating these sounds with the electrons. Well, it's creating the waves with the electrons.
It's creating an electromagnetic.
And that signal is sent out at a frequency, which is then, so all our antenna has to do is pick up that frequency and transmit it.
That is correct.
So, okay.
Yeah,
Okay.
good question. Right? Okay, sine wave. The sine curve can be traced by what's called simple harmonic motion. Now this is simple harmonic motion, right? Where like a pendulum on a clock, right? I pull the pendulum to one side, let go, and it just oscillates, right? And you'll find that for a given length of pendulum, it has the same frequency of oscillation. If I want a different frequency of oscillation, I have to change the length of the pendulum, right? So this is simple harmonic motion. Now simple harmonic motion traced through time will give you a curve like that, or the one above, right? That's the point that this down here is making. Okay, next slide. Continuing with waves, right? So here is a pond with water, or your swimming pool. Drop a pebble in it, and what happens is the pebble creates a disturbance that goes outwards in ripples, right? In circular patterns. Looking from the top down on these ripples, you see a pattern that looks like this, where this is a peak, that's a trough, that's a peak, that's a trough, that's a peak. Over time, these ripples move outwards, right? If you look at the ripples here, they're moving outwards as a function of time. So defining a few things. Frequency at the top there is vibrations per second. How many times will I vibrate per second? That's the frequency. Hertz is unit of frequency. 1 vibration per second is 1 hertz. 2 vibrations per second is 2 hertz. 10 vibrations per second is 10 hertz. The period is the time to complete 1 vibration. So how long does it take for me to finish 1 whole cycle? That's the period. The wave speed is the speed with which the wave passes a given point. So if I happen to be sitting here and I say, how fast are the waves traveling past me? That is the wave speed, right? And here's the relationship between frequency and the period. The frequency is equal to 1 divided by the period. Remember, the period is in time. It takes 2 seconds to finish 1 whole cycle, right? So just as an example, the period of the moon moving around the earth is what? 28 days, maybe 30 days, right? So if you look at the moon as it travels around the earth, it's approximately 28 days or some number like that, right? So it travels around the earth, so its period is 28 days. So the frequency of the moon will be equal to 1 divided by 28 days. You can convert it into hertz if you want, in seconds and so on. The next relationship is that speed is equal to frequency multiplied by wavelength. So frequency multiplied by the wavelength will give you the speed of the wave. Slide number 3. Okay, introducing the concept of a transverse wave compared to a longitudinal wave. A transverse wave, if you look at a snake, I happened to be on a walk, maybe during a walk that I was taking about 2 weeks ago. I saw this thing going like this across the path. Turns out it was a snake, right? So, how many of you have seen a snake in motion? Right? So, does a snake in motion look like a longitudinal wave or a transverse wave? Does the snake travel like this, or does it?
Transverse.
Yep, like a transverse wave. So, the way a snake moves like this, right, is how a transverse wave looks. The oscillation of the matter is perpendicular to the direction of motion of the snake, direction of motion of the wave. That's transverse. In the case of a longitudinal, how many of you have seen an earthworm move? Okay, so quite a few of you. The earthworm, as you may have noticed, does not move like a snake, right? What does the earthworm do? It kind of stretches out its front, grabs onto something, then sucks in its behind, right? Then stretches out its front, grabs onto something, right? And so you can see that it elongates, contracts, elongates, contracts, elongates, contracts. So completely different method of motion for an earthworm compared to a snake. So the way an earthworm moves is a longitudinal wave. In the case of a longitudinal wave, the pressure oscillation is in the direction of the motion of the wave. So if you had a string that is attached to a wall, it's easy to create a transverse wave. You grab the end of the string and you oscillate it up and down. It's pretty hard to create a longitudinal wave with a string, right? But you could create a transverse wave.
So, I don't even know if this applies, but like, just on the last slide we were looking at like water and the waves that go out from the center.
Okay.
Would you categorize that as one of these types of waves?
You could, yes.
Transverse? Because it
Good.
goes kind of up and down?
Yep.
Okay.
Good.
Because you're looking at the surface of the water, right?
Yes.
Okay.
Yeah, so each molecule, as the wave goes past the molecules of water here, they end up moving up and down.
Okay.
So the wave is moving in this direction, the motion of the matter is perpendicular to the motion of the wave.
Okay.
Now, if the matter were moving back and forth, it would be a longitudinal wave, right? So to first approximation, your answer is completely correct. Okay, next slide. Okay, waves with different frequencies. Again, we've got a clothesline that's attached to the wall. I oscillate it once per second. So it's 1 hertz. Once per second, 1,000, 2,000, 3,000, or 1 Mississippi, 2 Mississippi, 3 Mississippi. And I end up with a frequency of 1 hertz. And let's say that I end up with a wave that looks like this. The places where the string in this case does not move away from the 0 axis, the x-axis, is called the node. That's a node, that's a node. The places where, okay, it's not listed on this, but the places where there's a maximum amplitude is the anti-node, right? The anti-node is the maximum oscillation. Now, this is with the frequency of 1 hertz. If I double the frequency, instead of saying 1 Mississippi, I do 1 Mississippi, right? So 2 oscillations in that 1 second, I end up with a wave that looks like this, where here's the peak, here's the trough. Frequency of 2 hertz. If I increase the frequency further to 3 hertz, right? 1 Mississippi. By the time I say 1 Mississippi, I've oscillated 3 times. Well, to a first approximation. I end up with a wave that looks like this: peak, trough, peak. So this is actually 3 half waves, because the whole wave is from here to here, right? Because this point going upwards is not equivalent to this point, because it's going down. This point going upwards is equivalent to this point, which is going upwards. Now, a standing wave is a stationary wave pattern that's formed in a medium when you've got 2 different waves that interacting with each other. So standing, sometimes you can actually see this in practice, where you can actually see water creating, I mean, there are experimental setups that you can use to send 2 waves in, and the water will actually stand up in a heap, right? Just quite striking. That would be a standing wave. Okay, talking about 2 waves interacting with each other, we're now on slide number 5. We introduced the concept of interference, right? You all know in football or whatever, interference. Okay, I'm not very much of a sports geek or a sports aficionado, so you can correct me if I'm wrong. But a person is, or basketball, what is interference in basketball? There is no interference in basketball. There is interference in football, right? Right? Like, person is trying to get the ball in one direction, the other person comes and interferes, stops the process in some fashion, right? And I know that if you interfere in the right way, it's a good thing, and if you interfere in the wrong way, you get penalized, right? So, In the case of waves, when you have two waves, one of which is interacting with the other wave, that's called interference. So here's an example. We have one wave and there's another wave. Add the two of these up, they're exactly the same shape and size and they're in phase, right? They both have the peak where one has the peak where the other has the peak. One has a trough where the other has a trough. You add them up, what happens? They reinforce each other. So the peaks become higher here compared to here, right? Now if the two waves, so this is called constructive interference. They're constructively interfering. They're helping each other to reach a greater height. If you were to shift one of the waves so that the trough of this wave matches the peak of the other wave, this trough will exactly compensate for the peak. And in this case, this peak will compensate for that trough, and together they'll cancel out so that you don't have any oscillation, right? This is if these are perfectly done. So that is called destructive interference, where they're canceling each other. Now, if you had two sources, right? Think of the ripples in water. So if I had like a stone that I'm oscillating back and forth, and I keep creating these ripples going out, I do the same thing here with another one. So we got ripples going out here, ripples going out here, and where they interact, you can see that there are some places where there's increased intensity, right? Notice that the brightness is higher here, here, here. In these spots, you have constructive interference. Now notice here that they're canceling each other out. In a region here, you have lower oscillation, right? So the height of the oscillation here is twice the height of the oscillation of any one of these waves by itself. And in the dark band here, what happens is the oscillation is pretty close to zero. So you can actually see this in, so this is like a drawn schematic, versus this is a photograph of ripples on water, where you have two sources that are creating these water ripples going out, and you can actually see that they add up here. So you got a deeper trough and a higher peak, deeper trough, higher peak. Whereas as you travel along here, this is the maximum constructive interference. If I travel here, you can see this pretty close to no wave. You can't even see where the wave is. Because what happens is these two, the energy from these two waves, they're exactly cancelling each other out, right? So the interference pattern is created by superposition, right? The adding of the different sets of waves, which creates reinforcement in some areas and cancellation in some other areas. Okay, introducing the concept of Doppler effect. You probably all know what the Doppler effect is, right? Fire engine or a car that's traveling towards you and it honks. What happens to the pitch of the sound of the honk? It gets louder. What happens to the pitch? Loudness has to do with amplitude, the amount of sound coming in. What happens to the frequency of the horn? Frequency increases. So let's say you honk, right? As the car is coming towards you, instead of going what happens to the it goes right? Exactly. Extra credit. So once the car is past you, that's exactly what it does. It goes right? So as it goes away, the frequency is dropping. As it coming towards you, the frequency is increasing. That is the Doppler effect. So when the source of the sound, in this case the truck, is moving towards you, the frequency, the pitch increases. When the source is moving away from you, the pitch decreases. That is basically the Doppler effect, the change, the shift in frequency. And it's interesting that this Doppler effect effectively is what we use to determine the fact that the universe is expanding. If you look out at stars, what happens is, you've probably all seen a science fiction movie where, whatever, the spaceship Enterprise is traveling towards this star cloud. What happens to the stars in the cloud as the spaceship is moving towards them? Bunch of white stars. What happens to them?
They start getting above.
Yes, as you come towards them, you can see that feeling of getting closer to them as they move apart, right? What happens to the color of them? Have you ever noticed? They become what? Never looked? Last time we were in the Enterprise, we were like paying attention to something else.
On the holodeck.
Oh, I see. Okay. Brighter is one thing, but something happens to the frequency of the light. Stretched out, that's okay. What happens to frequency? The stars start looking a different color. I'll give you a hint. It's a 4-letter word. Yep, good job. Now, this is when you're traveling towards the stars, right? They get blue shifted. It's called blue shifted. The light, white light, is getting shifted to a higher frequency. It becomes more bluish. What happens to the color that's in the direction?
Red?
Yep, it gets red shifted. So if you look back, the stars that were red now start looking, they were white, start looking red, right? So in principle, and I'm willing to come to court in your defense if it comes to this, in principle, as you travel towards a red traffic light, the fact that you're traveling towards it will shift the frequency of the light upwards. So in principle, that frequency of light could get shifted so that a red light appears to be green. Isn't that amazing? There's only one small problem with this.
You have to be going extremely fast.
You have to be traveling at something like half the speed of light.
In which case you're in big trouble anyway.
Yeah, you're in like much bigger trouble than having...
Go that fast, how are we going to catch you though?
That's true. Well, good point. Yes. Yes, sir.
As you're, say that same scenario, and say you're in space, and you're headed towards the star, just like watching the star the whole time, in theory it could just disappear, right? Because light is so much further ahead of, it's still giving out light even after the light is gone from the source, because of light still traveling through space. I've heard that it takes light from the sun 8 minutes to reach Earth.
Correct.
So we wouldn't know that the sun went out until 8 minutes afterwards.
Correct.
So if you're headed towards a star and you're watching it, all of a sudden it could just disappear, right? Once all the light passed you, it would just be nothing.
That's true. If the star ceased to exist.
Yeah.
So I'll give you an example of this. I think there's a supernova called 1987A. I may be off on the number, right? So it's like 1987A. What happened is 1987, up to that point we have all these photographs of the night sky showing a star there. Then the star went bluey, right? It blew up. And then after it blew up, it disappeared. There's nothing to be seen, just like some remnants that were not hot enough for us to be able to see them, right? So the star ceased to exist because it blew up in 1987. But that star, if I recall correctly, is like 100,000 light years away from us. Which means it really ceased to exist 100,000 years in the past. It blew up 100,000 years in the past. But after it blew up, there's this stream of light that had been emitted, right? That still for another 100,000 years is coming to us.
That's funny. I read something like that on Facebook. There was like this post that said, if aliens 6 million light years away are looking at us right now, they're actually looking at the dinosaurs or something.
Yeah, they would be looking at it would have to be 63 million light years away, ballpark, right? Okay. But you're on the right track, right? So that is true. Except they'd be so far away that they couldn't resolve the dinosaurs.
Not enough detail.
They wouldn't be able to see enough detail in the light coming out of us, right?
Not according to art.
I'm sorry, what?
Not according to art. An alien civilization that's advanced enough to be able to see the Earth from 68 million light years away.
You think should have the resolution? Very, very possible, in principle, right? If you don't hit some fundamental limit, theoretical physics limit. Along those lines, show of hands. Okay, I don't mean to put you on the spot, but maybe I'll do it anyway. How many of you believe that there is ET out there? There is extraterrestrial, intelligent life on some other planet out there? Show of hands. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 9 of you. Question?
You mean like it has to be intelligent 100% as a possibility?
I mean, intelligent life as distinguished, different from bacterial life somewhere. That's what I'm. Okay, cool. I'm just.
Like microbiotic life out there. There's no way there is.
Okay, extra credit assignment to all of you for what is your reasoning to come to the conclusion. We can just put it on the website, right? Why do you come to the conclusion? Whatever conclusion you come to as to whether there's life out there, intelligent life.
You're talking about in general, not specifically little green men with big heads and big eyeballs.
It's okay if they're purple and they have really lots of very tiny eyes all around their belly button. That's okay. How about this? I will tell you the answer to that question after you guys have put in your answer, because I don't want to influence you. Right? Okay. I do have a view on it with reasons.
You're so influential. Was that sarcasm?
I don't know what that was. I think I think